All right, welcome back everybody. So we've been talking about how to solve these systems of linear differential equations using eigenvalues and eigenvectors. And now I'm going to show you one of my favorite versions of this system, which we call a saddle point. So if the A matrix has this form 1, 0, 0, minus 1, we're going to call this a saddle. And I actually don't even need to compute the eigenvalues and eigenvectors of this matrix because it's already diagonal. Okay, so we don't need the t and the d and the t because this matrix is already diagonal. And since it's already diagonal, we know, for example, that the eigenvalues of this A matrix are just the diagonal entries. So for example, the lambdas are going to be plus and minus 1. The eigenvalues of this system are going to be plus and minus 1. And so the building blocks of my dynamics are going to be things like e to the plus t and e to the minus t solutions. Okay? And since this is diagonal, we can kind of just write down the solution and write down and draw the picture, kind of the phase portrait of what trajectories look like in this system. And I'll give you a bunch of examples of systems that have these dynamics. This is actually one of the most prevalent types of dynamics for physical systems. So if you think about an inverted pendulum that's unstable, it's going to have this linearization. It's going to look like this for small angles. Me as a human walker is approximately an unstable pendulum. I'm feeling kind of stable today, mostly stable, but in general, we are unstable pendula, and so our local linear small angle dynamics are going to look like this. These crop up all over the place. These exist as fixed points in the solar system. So we just sent the James Webb Space Telescope to a point in the solar system that has these local dynamics. So that'll be kind of cool. I'll show you all of those examples. But let's write down the solution here. And so I'm just going to be very explicit by what I mean by this differential equation. Maybe I'll do this in green because it'll look cool. So I have d dt, and this vector x, let's say it has a component x and y. And sometimes I overload notation. I'm notorious about doing this. I always overload my notation. So bold x with an underbar is a vector. And it contains two components, little x and little y, the x component and the y component. And I hope you're okay with the fact that this little x is just one of the components of this vector x, okay? Sometimes I would call this x1 and x2, but I just want you to be comfortable with different ways of writing notation. Kind of, this is what you call an abuse of notation. We're abusing our notation, but it's okay. And so dx dt and dy dt equals this matrix system 1, 0, 0, minus 1, 1, 0, 0, minus 1 times x and y. And again, because this is already diagonal, I can just write down the matrix solution. I can take the matrix exponential of this easily, and I can write down that x of t and y of t, my state at time t, is going to equal e to the positive t, 0, 0, e to the negative t, times my initial conditions x naught and y naught. You say, why not? I can give you a million reasons why not. And what this means is that these, again, are completely diagonal and decoupled. So x of t, essentially what this means is that, x of t equals e to the t x naught, and y of t equals e to the minus t y naught. So the x direction is massively unstable. If I start with a little x naught, it's going to blow up, and go off to infinity and grow and grow and grow. And if I start with a little y naught, a little initial condition in the y direction, it's going to decay to 0 because this is a stable e to the minus t. And so we can draw this phase portrait. This is called a saddle point. This is called a saddle point. And I'll tell you why it's called a saddle in a minute. It's kind of literally like if you drop a marble on a saddle, it'll have these dynamics I'm about to show you. A lot of the naming in math is kind of old-fashioned. I think it's funny that there's an algorithm in statistics called the lasso. This is called a saddle point. There are horseshoe orbits. So kind of all of this old-timey cowboy stuff crops up in the naming. And so I'm going to draw this thing again in the x y coordinates and my x and y coordinates. And it's kind of exactly like what I just told you. So if I start with an initial condition that has only an x naught and y naught is 0, so I start with some initial condition, here or here. So y is 0, but I start with some x naught. These are going to grow without bounds because e to the plus t is unstable. So I'm going to draw a plus kind of, oof, that's ugly. I'm going to draw an unstable arrow in the x direction. Kind of, if I start with positive x, it's going to become more and more and more positive. If I start with a negative x, it's going to become more and more and more negative. It's going to be unstable in x. And similarly, if I start with a little initial condition in y, either of these, but 0x, if I start exactly on this y-axis, these dynamics are going to be stable and they're going to contract. So a little y naught is going to get smaller and smaller and smaller as time goes on. And so these arrows are going to be pointing inward. And so the x-axis and the y-axis for this problem are, in fact, the eigenvectors of this matrix because it's already diagonal. So the eigenvector corresponding to this eigenvalue 1 is the x direction. The eigenvector corresponding to this eigenvalue -1, the stable eigenvalue, is the y direction. And so if I start exactly on that x-axis, I will stay on that x-axis and grow without bound. If I start exactly on that y-axis, I will stay on that y-axis and my trajectory will shrink to the origin. Again, we have a fixed point at the origin. If we started exactly at x equals 0, will stay at x equals 0 because a times 0 is 0, and so ddt of x would be 0 at that point. No forces pushing me one way or the other. But what's really interesting is looking at what happens, if I take some initial condition that's not on one of these axes. Let's say I take an initial condition here. What's going to happen is in the y component of this is going to shrink and shrink and shrink and shrink and shrink, and it's going to keep shrinking forever because it's completely decoupled. The y component is always going to get smaller and smaller, but at the same time, maybe I'll start over here. At the same time, the x component is going to grow and grow and grow and grow exponentially. And so I get trajectories that kind of shrink in the y direction as they grow in the x direction. And over here, since this had a negative x naught, it's going to shrink in the y direction. And again, x is going to get bigger and bigger and bigger in that negative direction. So I have these kinds of orbits here. Similarly, down here, y is going to get smaller while x increases. Down here, y is going to get smaller while x increases. Okay? And so this is what the phase portrait of a saddle generically is going to look like. It's going to have everything kind of compressing in one direction and stretching out in the other direction, okay, which is kind of cool. This is almost like if you were making taffy, you'd be, pulling that taffy, it would get thinner in one direction and longer in the other direction. So people actually model mixing and stretching and folding using saddle point dynamics and things like that. So this is the kind of pretty picture you get for saddle dynamics, where you have one unstable direction and one stable direction. Anytime your system has any unstable directions at all, even a single unstable direction, means your system is unstable. So a saddle point is, in fact, unstable. So maybe I'm not as stable as I thought I was. And this is a very, very important fixed point or type of dynamical system that's going to come up a lot. So I'm calling these dynamical systems because they change in time. X dot means dx dt, how x changes in time. So this is literally the path I would take in time if I started with this initial condition. I'd flow forward in time. Okay. One of the cool things about saddles is if I reverse time, they are still saddles. If I reversed all of these arrows, it would just change which of x and y is stable and unstable, but it's still a saddle point. Something that's kind of neat that I'm going to show you in the next few lectures, not the next one, but probably the one after that, is that even though we're looking at very idealized linear systems, and we know that most of the real world is not linear, like the pendulum, right? Like a pendulum swinging is only linear for very small angle approximations, but for large angles, it's nonlinear. Theta double dot equals minus sine of theta, and sine of theta is a nonlinear function. Most of the systems we care about are actually nonlinear. The astrophysics, planetary problems, that's nonlinear physics. But there exist these fixed points, like this one here, where x dot, so if maybe x dot equals some generic nonlinear system, f of x, where this is not linear, it's not a matrix times x, maybe it's x squared and it has cubic terms and it's nasty, or sines of x. But there are often fixed points fixed points where f of x equals 0. And so what you can do in these systems is you can kind of zoom in near that fixed point. The dynamics are going to locally look linear, and they're going to have these kind of canonical behaviors. They're going to either be saddles or sources or spirals, or I'm going to show you all of the kind of types and menagerie of fixed points that you can have, at least in 2 dimensions. And we're going to use those as building blocks. Even in very nonlinear systems, you're going to be able to piece together kind of the geometry of that phase space of how trajectories move in these x and y coordinates based on kind of understanding these building blocks, these saddle points and center points and stable points and things like that. Okay, so that's all coming up, and a saddle is a really, really important one of these. Okay, so I'll give you a couple of other examples. Let me pick a couple of colors here. So some examples of saddle points that I like. Examples of saddle points. Or examples of systems that have these saddle fixed points. That's more what I mean. These are going to be nonlinear systems, but some of the fixed points are going to have this local saddle behavior that if you zoomed in, there would be an unstable and a stable direction. So I already told you one of my favorite examples is, a person walking. Maybe they're dancing, I don't know. But if you think about it, so you can't see my legs, but I'm standing on my tippy toes so I can feel unstable. And if you like shot Novocaine into my ankles, I would be pretty upset and I'd fall over because I am an unstable, kind of like a pendulum, right? Like, so you have a pendulum in its stable position and it just swings down, but you could bring that pendulum up into the upright position. And if you balance like a broom on your hand, that's an unstable pendulum, and that has these saddle dynamics. And a human, this is, I've drawn them standing, I've drawn them standing in a very stable position, but if you stood on one foot, maybe I can do this better. If I stand on one foot, that's better. That's much better. Then on that one foot, I'm much more like a saddle point, because I have this kind of fundamental instability that if you kick me a little bit in one direction, I'm going to accelerate in that direction and go unstable. Okay, at least locally, that's going to be true. And actually, you can think about this as your arms are kind of the stable direction. When you're walking in an efficient gait, your arms are actually stable. If I just do this, they're not going to blow up to infinity. They're stable, and eventually they'll die out. But the body part and your legs, that's this unstable direction that if you kicked yourself, you'd go unstable. And a theme in differential equations and dynamical systems is that having a little bit of instability is actually very good for efficient maneuverability. So if you think about how we walk as humans, bipedal walkers, all I have to do to move forward is kick myself a tiny bit in my unstable direction. I just lift up one foot and I go a tiny bit in that direction, and gravity takes care of the rest. It moves me a lot in that direction, and then I put my foot down and I kick myself a little bit in the unstable direction with my other foot. And so very, very efficiently, I can harness this kind of unstable direction to get a lot of forward motion for cheap. Okay? This is actually how fighter jets turn so efficiently, is that they're kind of natively unstable, and they use control systems to just barely stabilize themselves so that they can turn on a dime. So these saddle points, if you think about it, if I wanted to have really energy efficient control, I want to be kind of just on one side of a saddle point, because if I'm right here and I kick myself a tiny bit to the left or a tiny bit to the right, I spend a tiny, tiny little bit of energy, I can go to completely different locations. So I get a large kind of gain for a small input in these saddle type systems. That's how humans walk very efficiently. That's how planes, fighter planes, turn very efficiently. So that's kind of cool. That's one example, is a person walking, and I like to say that this is, efficient locomotion. Efficient locomotion. Good. That's one. And a second one that I like to talk about is why it's actually called a saddle point in the first place, is because you can imagine, I'm going to have a really hard time drawing a saddle, but you can picture a saddle that you would put on a horse. And the saddle that you would put on a horse has a part here that goes up. So this is kind of where your butt goes, and this is the pommel. That's called the pommel of the saddle, where you hold on. And then on either side, it kind of drops off, and I'll draw this one back here. Okay, so this is kind of like the saddle you would put on a horse. This is why this is called a saddle point. And if you picture putting a bead or a marble on this saddle and rolling it, it kind of behaves the way that this would behave. So at least locally, if I perfectly lined my marble up so it was exactly on this ridge, kind of here, it would actually be stable in this direction. It would approach, kind of the center. And if there was a little friction, it would eventually die out. This is an idealization. Of course, it's not actually going to do that. But if I started my bead, sorry, I should be down here. If I started my bead down here on this kind of stable direction, it would kind of just slowly eventually die out at that point. But if I kicked it a little bit off in this kind of unstable saddle direction where your legs go, then it's going to roll off and go to infinity, to hit the ground. Okay, and so this is why this is called a saddle, because a saddle kind of, if I dropped a bead on it, it has one stable direction and one unstable direction, where, if I roll it in this way, it falls off. If I roll it in this way, it kind of stays put. Okay, that's why this is called a saddle. Now, funny, you might ask, is that there is actually something called a monkey saddle in dynamical systems, which I really like, which is a saddle, but it still has a place for your legs here, and it still has a pommel, but it has a place for the monkey's tail. So instead of the back going up, this is kind of like a cubic function, and it has a place for the monkey's tail. This is called a monkey saddle. I don't know why I'm telling you this, I just find it fascinating. Okay, so that's another interesting example, is an actual, bead on a saddle, like a marble on a saddle. Sometimes I'm going to call this a bead. By bead, I mean a marble or something that rolls or slips with no friction. A bead on an actual saddle. A saddle, like the saddle you'd put on a horse. And then one of my absolute favorite examples of this, the one that kind of got me really inspired, one of my first research projects as a freshman undergraduate at Caltech, was this problem of planetary dynamics. Planetary dynamics. And I've been actually very fortunate to have learned this dynamical systems material is some of my favorite stuff, eigenvalues and eigenvectors and fixed points and phase portraits. You can tell I love this. I've been doing this, again, since I was an undergraduate. I've had the pleasure of learning this from some amazing people like Jerry Marsden and Wang-Sang Kuhn were my instructors. I learned a lot from Sean Shadden and Shane Ross. Later on, I learned from Phil Holmes. So it's really been amazing to kind of soak up that knowledge from those excellent people, and I love sharing it with you. So I'm hoping a lot of what they taught me comes through in these lectures. And when I was an undergrad working with Jerry Marsden and Wang-Sang Kuhn, it was a really exciting time because people were so planetary dynamics, like how moons orbit planets and how the planets orbit the sun, and predicting the motion of all of these celestial bodies, that's been something that's fascinated humans since before written history. Okay, for all of history, people have looked up at the sky and wondered why planets do the things they do. We name our gods after planets and our planets after gods because planets do cool stuff that's unpredictable and chaotic. And in the kind of early 2000s, there started to become some really new machinery being developed, some new mathematical machinery to understand energy efficient transportation in the solar system. And so I'll tell you just kind of a teaser story about that I thought was really cool. So we have the sun, and I'll try my best to make it sun colored. So this is the sun. It's awesome. And let's say we have Jupiter. Okay, I'm going to make Jupiter, what color should I make Jupiter? Why not pink? So Jupiter over here. And we've known for a long time, since Poincaré in I think 1906, that if I have 3 bodies. So this is the 2-body problem. These are just going to go around in kind of Keplerian ellipses, right, orbits with each other. But if I had a 3rd body, then the dynamics of that system may be chaotic. That might be kind of unpredictable and chaotic if I add even a 3rd body here. And that 3rd body could be small. It could be an asteroid, it could be a satellite, it could be a spacecraft. In fact, we have chaotic transport of asteroids in the solar system right now. Which is interesting. And it turns out that there are these very, very special saddle fixed points that exist in this planetary system. In this 2-body problem, there is a saddle point here, and there is a saddle point here. And these are called the Lagrange points, the L1 and L2 Lagrange points. There's an L3, an L4, and an L5. There's 5 Lagrange points for this system. But these two have a very special property of having at least 1 degree of freedom that behaves like a saddle. One last thing I need to draw here is that there is a kind of a potential energy forbidden region in this system. So if I was an asteroid, or if I was a spacecraft and I only had a certain amount of energy, of kind of kinetic energy, there would be a region that I couldn't access. I could not occupy this region because I don't have enough energy. And this is actually a really good thing, because this means that a lot of asteroids from the outer solar system beyond Jupiter don't have enough energy to kind of get into the inner solar system. And so Jupiter is actually acting like a referee or a goalkeeper for asteroids for the inner planet. So it's protecting us on Earth from outside objects coming in and just creaming us, okay? And so the only way that objects can actually come into the inner solar system, the asteroid is the 3rd body in this 3-body problem. So the Sun is the massive one, Jupiter is also pretty massive, and then the 3rd body we assume to be massless, but influenced by these, and that's a chaotic dynamical system. So like an asteroid, the only way it can come in is around these saddle points. There are these very special orbits that will take objects into and out of the inner solar system through this kind of Jupiter transit. Sometimes this is called a turnstile, but really Jupiter and these saddle points is mediating most of the structure of transport between the inner solar system and the outer solar system, which is really, really cool. I'm pretty sure researchers have found in the last few decades there is an extremely high proportion of what are called twin asteroids, asteroids that are in kind of a binary orbit with each other, just moving around in each other's gravitational orbit in the inner solar system. And we believe that it's because they have to pass through this kind of gravitational turnstile and go really close to Jupiter. So all of the asteroids that make it in kind of get bunched up here, and they start to orbit each other, and they stay orbiting each other in here, which is really, really interesting. Some estimates are that like 10% of them are paired up through these turnstiles. That's wild. But what I really wanted to point out is that, it's not just the Sun and Jupiter. Every pair of kind of primary bodies has this structure. So the Earth and the Moon also have these saddle points. This fixed point's really easy to understand. This fixed point here and here is really easy to understand. That's the equal gravity point, where if I'm right, there's a sweet spot between the Earth and the Moon where their gravitational pull is exactly equal. And if I was right there, I'd stay there forever. But if I move a little towards the Moon, I'll fall into the Moon's orbit. And if I move a little towards the Earth, I'll get sucked into the Earth. That's a fixed point that has an unstable direction, obviously. That's one of these L1 points. I think that's L1 and this is L2. And so these guys also have those saddle points. We just sent the James Webb Space Telescope to live right around this L2 point. Is that right? No, not this L2 point, a different L2 point. So the Earth and the Moon have one. The Sun and the Earth also have these. So kind of every primary pair, the Sun and Jupiter has these points, the Sun and the Earth has these points, the Earth and its Moon has these points. And so what's really interesting is that these saddles allow me to transition in very energy efficient ways around the solar system. So for example, if I'm on one side of this saddle, I can push myself a little bit and go into the inner solar system. And if I push myself a little bit on the other direction, I'm going to go to the outer solar system. So these fixed points are very, very important for energy efficient transport in the solar system. If we want to design a space mission, for example, that goes to all of the moons of Jupiter, we can do that with very little energy by looking at all of the fixed points of each of the Jupiter moon systems, each of these fixed points for Jupiter and its moon, and we can find kind of orbits that get close to other fixed points of other moons and connect those together with really small amounts of energy burn. And so it's really interesting that the skeleton of our solar system is built out of these saddle points and the orbits that emanate from those saddle points. And that kind of connects the solar system in this kind of freeway network of really energy efficient transport. And it organizes all of the trajectories in the solar system. Very nonlinear system, hugely nonlinear. It's really, this f of x is very nonlinear for the solar system, very chaotic. But there exist these fixed points where locally, for a small radius, they have these saddle dynamics. That's kind of the upshot here I want to get across. Good. Yeah, so we can use those for energy efficient transportation in the solar system. It's also how Jupiter protects us from objects coming into the inner solar system. And I think the last thing I wanted to tell you, I believe it's the Sun-Earth system. I think that what we did is we put the James Webb Space Telescope in what's called a halo orbit around the Sun-Earth L2 point, because this is super cool. So a halo orbit, it's because it looks like a halo, like an angel's halo, and it blocks the light from the sun. So this is kind of protected from the light from the sun by the Earth, and so it's always in the shadow of the Earth, which means that it has a lot better sensitivity for its detectors. It's not being bombarded by sunlight, so it can look out at all of the stars out there without getting contaminated by all of this electromagnetic spectrum. I think it must be the Sun-Earth L2. Put in the comments if I'm mistaken. But this just launched. We've been waiting for this I've been waiting for this for well over 10 years to happen. It just happened. We just got images back, and it's amazing. The power of saddle points in the solar system. Okay, next lecture I'm going to tell you what happens when these have complex eigenvalues. That's going to be super interesting, and we're going to use Euler's formula to take e to the lambda t's and break that into sines and cosines when that lambda is complex. So that's all coming up next. Thank you.